When upgrading to a 200 amp service, several factors regarding conduit size, breaker selection, and overcurrent protection need consideration. Firstly, the existing 1.5-inch conduit is insufficient for the upgraded service. The National Electrical Code, commonly known as NEC, dictates the minimum conduit size required for specific conductor sizes and configurations. For 3/0 American wire gauge, commonly known as AWG conductors, particularly when the conduit run includes bends like 2 or 390-degree bends, a 2-inch conduit is required to comply with the NEC. Now, regarding the breaker and main overcurrent protection, commonly known as MOCP, the existing configuration presents a non-compliance issue. The MOCP is rated at 175 amps, while the breaker feeding the circuit is rated at 200 amps. The NEC mandates that the MOCP, whether it is a fuse or circuit breaker, must be rated at or less than the breaker protecting the circuit. In simpler words, the MOCP should not exceed the rating of the upstream breaker. To address these issues, firstly, the existing 1.5-inch conduit needs to be upgraded to a 2-inch conduit to meet the NEC requirements for conduit size based on the 3/0 AWG conductors and the presence of bends. Secondly, the existing MOCP rated at 175 amps needs to be replaced with a 200 amps breaker. This ensures that the MOCP matches the rating of the breaker feeding the circuit, bringing the installation into compliance with the NEC. An additional but crucial point is to ensure that the wire used is rated for the ampacity of the circuit. In this scenario, 3/0 AWG wire is suitable for a 200 amp circuit. Ampacity refers to the current carrying capacity of a conductor, and it must be adequate for the intended load. The NEC provides tables and guidelines for determining the appropriate wire size based on the circuit's ampacity and other factors such as insulation type and installation conditions. So, to summarize, firstly, verify the conduit size is adequate for the conductors being used, ensuring compliance with the NEC based on wire gauge, conduit fill, and the number and type of bends. Secondly, confirm that the MOCP rating is equal to or less than the rating of the breaker protecting the circuit. Thirdly, ensure the wire is rated for the ampacity of the circuit, selecting the appropriate wire gauge based on the anticipated load and NEC guidelines. Always consult the most recent edition of the NEC and local electrical codes for the most accurate and up-to-date information. Electrical work should only be performed by qualified and licensed electricians who are familiar with applicable codes and safety procedures. Now let's delve into a deeper explanation behind these requirements. Firstly, the conduit size is governed by NEC Article 300.17, which addresses raceways and cable trays for conductors. The NEC specifies the maximum percentage of cross-sectional area of a conduit that can be occupied by conductors. This is to ensure adequate space for heat dissipation and ease of pulling conductors during installation and future maintenance. For 3 or more conductors, the maximum fill percentage is typically 40%. Using a conduit fill calculator or referring to NEC Chapter 9, Table 4, one can determine the appropriate conduit size for a given number and size of conductors. In this case, 3/0 AWG conductors require a larger conduit than 1.5 inches, especially with multiple bends, due to the increased pulling force required. The bends introduce friction, making it harder to pull the conductors through the conduit. As for the breaker and MOCP considerations, the NEC addresses overcurrent protection in Article 240. The purpose of overcurrent protection is to protect conductors and equipment from excessive current which could lead to overheating, insulation damage, or even fire. The MOCP serves as the primary means of overcurrent protection for the circuit. If the MOCP is rated lower than the breaker feeding the circuit, it creates a situation where the breaker might not trip in time to protect the circuit in the event of an overcurrent condition. For instance, if a fault occurs and the current exceeds 175 amps but remains below 200 amps, a 175 amps MOCP should trip to interrupt the circuit. However, with a 200 amps breaker upstream, the breaker might not trip, potentially damaging the conductors or equipment connected to the circuit. The NEC requires that the overcurrent protection device be selected and coordinated to protect the circuit components. This means that the MOCP must be sized appropriately based on the ampacity of the conductors and the rating of the equipment being protected. The general rule is that the overcurrent protection device should not exceed the ampacity of the conductors it protects, as specified in NEC Table 310.16. Regarding the wire ampacity, 3/0 AWG conductors are commonly used for 200 amp circuits, but it's essential to verify the ampacity rating based on the insulation type and installation conditions. NEC Table 310.16 provides ampacity ratings for various conductor types and sizes. For example, 3/0 AWG copper conductors with THHN insulation installed in a raceway or cable typically have an ampacity of 200 amps at 75 degrees Celsius. However, if the conductors are installed in an environment with a higher ambient temperature, or if there are more than 3 current-carrying conductors in the raceway, the ampacity might need to be derated according to NEC Section 310.15. Derating involves reducing the allowable ampacity of the conductors to prevent overheating. Furthermore, voltage drop is another consideration when selecting conductors. Voltage drop refers to the reduction in voltage along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. To minimize voltage drop, larger conductors or parallel conductors might be necessary, especially for long circuit runs. In the context of the service upgrade, it's crucial to ensure that all electrical components, including the panel board, breakers, and conductors, are rated for the upgraded 200 amps service. The panel board must have a main breaker or fusible switch rated for at least 200 amps, and the branch circuit breakers must be sized appropriately for the loads they serve. Furthermore, all connections must be properly torqued to ensure a secure and reliable electrical connection. Loose connections can lead to overheating and electrical failures. Moreover, grounding and bonding are essential for electrical safety. Grounding provides a low impedance path for fault current to return to the source, allowing the overcurrent protection device to trip and clear the fault. Bonding ensures that all metal parts of the electrical system are electrically connected, minimizing the risk of electric shock. The grounding and bonding system must comply with NEC Article 250. It is important to ensure that the grounding electrode system is properly installed and connected to the panel board. This includes grounding electrodes such as ground rods, water pipes, or concrete encased electrodes. In addition to the technical aspects, it's crucial to obtain all necessary permits and inspections before starting any electrical work. Local electrical inspectors will verify that the installation complies with the NEC and local codes, ensuring safety and preventing potential hazards. When upgrading an electrical service, it's often necessary to coordinate with the local utility company. The utility company might need to upgrade the service drop or transformer to accommodate the increased load. It's essential to notify the utility company in advance and follow their requirements for the service upgrade. Safety is paramount when working with electricity. Always to energize circuits before working on them, and use appropriate personal protective equipment, commonly known as PPE, such as insulated gloves and safety glasses. If you are not comfortable working with electricity, it's best to hire a qualified and licensed electrician to perform the work. Upgrading an electrical service involves careful planning and attention to detail. By following the NEC and local codes, and by using qualified professionals, you can ensure a safe and reliable electrical installation. Now let us review more about the code, specifically NEC 310.15. This section covers the ampacity of conductors, considering factors like temperature rating, ambient temperature, and the number of current-carrying conductors in a raceway or cable. The ampacity of a conductor is the maximum current, in amps, it can carry continuously under specific conditions of use without exceeding its temperature rating. The NEC provides ampacity tables, such as Table 310.16 and Table 310.17, which list the ampacity of various conductor types and sizes based on their insulation temperature rating and installation conditions. However, These ampacity values are based on specific ambient temperatures, typically 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature is higher than this value, the ampacity of the conductor must be derated. Derating involves reducing the allowable ampacity of the conductor to prevent it from overheating. The NEC provides adjustment factors in Table 310.15 to account for higher ambient temperatures. For example, if the ambient temperature is 40 degrees Celsius or 104 degrees Fahrenheit, the ampacity of the conductor might need to be reduced by a certain percentage depending on the conductor's insulation temperature rating. In addition to ambient temperature, the number of current-carrying conductors in a raceway or cable also affects the ampacity of the conductors. When multiple current-carrying conductors are installed in close proximity, they generate heat, which can raise the temperature inside the raceway or cable. This increased temperature can reduce the ampacity of the conductors. The NEC provides adjustment factors in Table 310.15b3 to account for the number of current-carrying conductors in a raceway or cable. For example, if there are 4 to 6 current-carrying conductors in a raceway or cable, the ampacity of the conductors might need to be reduced by 80%. It's important to note that the neutral conductor in a single-phase, 3-wire circuit is considered a current-carrying conductor if it carries a significant amount of current. This can occur when the loads on the two hot conductors are unbalanced. In such cases, the neutral conductor must be counted as a current-carrying conductor when determining the ampacity adjustment factor. When derating conductors for ambient temperature or the number of current-carrying conductors, it's essential to use the correct adjustment factors and apply them to the ampacity value from the appropriate NEC table. The derated ampacity must be sufficient to carry the load current without exceeding the conductor's temperature rating. Furthermore, the overcurrent protection device must be sized to protect the derated ampacity of the conductor. The overcurrent protection device should not exceed the derated ampacity of the conductor as specified in NEC section 240.4. The NEC also provides specific rules for conductor protection in certain applications, such as motor circuits and air conditioning equipment. These rules might require the use of specific types of overcurrent protection devices or the application of different ampacity adjustment factors. In addition to ampacity derating, voltage drop is another important consideration when selecting conductors. Voltage drop refers to the reduction in voltage along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. To minimize voltage drop, larger conductors or parallel conductors might be necessary, especially for long circuit runs. The voltage drop can be calculated using Ohm's law, which states that voltage drop is equal to the current multiplied by the resistance of the conductor. The resistance of a conductor depends on its length, cross-sectional area, and material. The NEC provides tables that list the resistance of various conductor types and sizes. When calculating voltage drop, it's important to consider the total length of the circuit, including the return path. The voltage drop should be calculated for the full load current of the circuit. If the calculated voltage drop exceeds the recommended limits, the conductor size must be increased or parallel conductors must be used. In some cases, it might be necessary to use a voltage booster to compensate for voltage drop, especially for long circuit runs or heavy loads. Voltage boosters are devices that increase the voltage at the load end of the circuit, ensuring that the equipment receives the proper voltage. The selection of conductors and overcurrent protection devices requires careful consideration of various factors, including ampacity, derating, voltage drop, and application-specific rules. It's essential to consult the NEC and other relevant standards to ensure that the electrical system is safe and compliant. Licensed and qualified electricians should be consulted for the design and installation of electrical systems. It is also important to consider conduit fill when installing conductors in a conduit. Conduit fill refers to the percentage of the conduit's cross-sectional area that is occupied by conductors. The NEC limits the maximum conduit fill to prevent overheating and to ensure that the conductors can be easily pulled through the conduit. The maximum conduit fill percentage depends on the number of conductors in the conduit. For one conductor, the maximum fill is 53%. For two conductors, the maximum fill is 31%. For 3 or more conductors, the maximum fill is 40%. To calculate the conduit fill percentage, you need to know the cross-sectional area of the conductors and the cross-sectional area of the conduit. The NEC provides tables that list the cross-sectional area of various conductor types and sizes. The cross-sectional area of the conduit can be calculated using the formula equals pi2, where is the area, pi is pi or approximately 3.14159, and r is the radius of the conduit. Once you have the cross-sectional area of the conductors and the conduit, you can calculate the conduit fill percentage using the formula conduit fill percentage equals total area of conductors slash area of conduit asterisk 100. If the calculated conduit fill percentage exceeds the maximum allowed, you need to increase the size of the conduit or reduce the number of conductors in the conduit. It's also important to consider the bending radius of the conduit when installing conductors. The bending radius is the minimum radius to which the conduit can be bent without damaging it. The NEC specifies minimum bending radii for various conduit types and sizes. The bending radius should be large enough to prevent the conductors from being damaged or stressed during installation. When bending conduit, it's essential to use the proper tools and techniques. Conduit benders are designed to bend conduit without kinking or flattening it. It's also important to avoid overbending the conduit, as this can weaken it. When installing conductors in a conduit, it's helpful to use pulling lubricant. Pulling lubricant reduces friction between the conductors and the conduit, making it easier to pull the conductors through the conduit. The NEC provides specific rules for the installation of conductors in conduits, including requirements for supporting the conduit and securing the conductors. Conduits must be supported at regular intervals to prevent them from sagging or becoming damaged. Conductors must be secured in the conduit to prevent them from moving or becoming dislodged. Proper installation of conductors in conduits is essential for safety and reliability. Incorrectly installed conductors can lead to overheating, insulation damage, and electrical faults. Additionally, ensuring the electrical system meets the required short-circuit current rating is paramount for safety and code compliance. The short-circuit current rating, or SCCR, indicates the maximum fault current that an electrical component or system can safely withstand. If a fault current exceeds the SCCR of a component, it could lead to equipment failure, fire, or even explosion. The NEC requires that all electrical equipment be marked with its SCCR and that the available fault current at the equipment's location be determined. The available fault current is the maximum current that could flow during a short-circuit condition. It depends on the source impedance of the electrical system, which includes the utility transformer, conductors, and other components. To determine the available fault current, a qualified electrical engineer or technician can perform a short-circuit study. A short-circuit study involves analyzing the electrical system to calculate the fault current at various points. The results of the short-circuit study are used to select equipment with appropriate SCCRs. The electrical equipment must have an SCCR that is equal to or greater than the available fault current at its location. If the available fault current exceeds the SCCR of the equipment must be protected by a current limiting device such as a fuse or circuit breaker. Current limiting devices are designed to quickly interrupt fault currents before they reach their peak value. They can significantly reduce the stress on electrical equipment during a short-circuit condition. The NEC provides specific rules for the selection and application of current limiting devices. It's important to choose current limiting devices that are compatible with the electrical equipment they are protecting. The selection of overcurrent protection devices, such as fuses and circuit breakers, is also critical for short-circuit protection. Overcurrent protection devices are designed to interrupt fault currents and prevent damage to electrical equipment. The NEC provides specific rules for the selection and coordination of overcurrent protection devices. Overcurrent protection devices must be sized to protect the conductors and equipment they are serving. They must also have an interrupting rating that is equal to or greater than the available fault current at their location. Proper coordination of overcurrent protection devices is essential to ensure that the device closest to the fault will trip first, minimizing the impact on the rest of the electrical system. Coordination studies are often performed to verify that the overcurrent protection devices are properly coordinated. The NEC also requires that all electrical equipment be properly labeled with its SCCR and other relevant information. This labeling helps to ensure that the equipment is properly installed and maintained. Regular inspection and testing of electrical equipment is also important for maintaining its short-circuit withstand capability. Over time, electrical equipment can degrade due to wear and tear, corrosion, or other factors. Regular inspection and testing can help to identify potential problems before they lead to equipment failure. Ensuring the electrical system meets the required SCCR is a critical aspect of electrical safety. By performing short-circuit studies, selecting equipment with appropriate SCCRs, and properly coordinating overcurrent protection devices, you can minimize the risk of damage and injury during a short-circuit condition. And as a reminder, remember to consult with qualified electrical professionals and adhere to all applicable codes and standards when designing and installing electrical systems.